All right, so let me thank the organizers for inviting me here. I'm very honored, and it's an absolutely marvelous place. I feel very at ease. So, so my talk is kind of related to what Daniel was talking about. He was talking about what happens below these minimum energy instanton type solutions, and I will be talking what happens above. So, it happens for a lot of the models that we care about, that you get very complicated dynamics with arbitrarily small energy excess above the minimum energy instanton already. So to start with, so very roughly speaking, I'm interested in so-called bubbling off blow-up solutions. My setting is more general. So let's say box use f of u del u is some kind of semi-linear nonlinear wave equation, which is Hamiltonian, has a conserved energy. And it admits a scaling symmetry, meaning that this transformation carries solutions into solutions. And I will roughly call a solution of this form. So it's a rescaled W. W is a function which only depends on the spatial variables. But it gets dynamically rescaled here. So lambda is a function of t. And provided that this function blows up in finite time, and moreover W is a finite energy solution, then I will call this a bubbling off singularity. Of course, this is not very precise. What I mean by this notation is that the solution decouples into a scaled bubble plus a radiation part, and the radiation part in a certain sense moves away. More precisely, if you take a backward light cone at the singularity, then the excess radiation gets radiated out, and in the light cone, you're left only with this part, which concentrates the energy of W inside this backward light cone. Now, many models display this form of blow-up. And experience has revealed that these types of blow-up play a very important role, specifically for energy-critical models. You may also construct such examples in certain energy supercritical models, but particularly in the energy-critical models, they play a very decisive role in the description of dynamics. What is an energy-critical model? It's one where the scaling transformation leaves the conserved energy invariant. So, for example, there is the wave maps equation that Daniel was talking about, R2 plus 1 into S2. If you use ambient coordinates, then you get this formulation. So, it's quite nice. It's a system, of course, of wave equations. And so this kind of model admits a W, a static solution. So for example, the stereographic projection, but there are infinitely many others covering all the homotopic classes. And we now know that all of these static solutions can be made to collapse by suitable small perturbations. And these collapsing solutions then are of this bubbling off form. And what's interesting is that we have also realized that there are infinitely many possible scaling laws, even if you just take the ground state bubbling off solution corresponding to W being the stereographic projection. You can take lambda of t to be any scaling law of this form, t to the minus 1 minus nu, where nu can be any positive number. There are solutions that can be made like this. Here I have to say, so for my solutions, I don't force them to be C infinity smooth before the blow up. So I'm taking the full spectrum of solutions of energy regularity, because this problem is well, it's strongly locally well posed in any regularity just above energy, and therefore, so I allow any solution of class H1 plus a little bit to be a good solution for my problem here. So then, on the other hand, there's the Young-Mills model, which Daniel talked about, and of course, under very special symmetry reduction, you can again reduce this to a much simpler semi-linear kind of problem. So I just take this at face value here. So this is now actually a 2 plus 1 dimensional problem under suitable symmetry reduction. And again, there is your W as this function here. R is, of course, the length of X. And again, for this kind of problem, you have these bubbling off blow-ups. And there's again, if you work with solutions of general energy regularity, you can put lambda of t is equal to t to the minus 1 times log t to some power. If beta is bigger than a certain constant, you can construct, so there's again infinitely many scaling laws in this. And then finally, there's this equation here, which is the most important for my talk. That's the energy critical focusing nonlinear wave equation. It's the analog of the model that Colo talked about. However, the wave analog, and it's in 3+1 dimension, so it's in relatively low dimension. And again, you have a W, which is the famous Oberanta-Lenti solution here, and this solution leads to blow-ups. And again, for this model, strangely enough, we have the same kind of spectrum of possible speeds here. Any t to the minus 1 minus nu, and in fact, you can have more general laws here. So you can also have solutions with t to the minus 1 minus nu times e to the epsilon sine log t. So you can have a little bit of, actually not e to the, so you can just build that in here. So it's minus epsilon times sine log t. Can build things like that. So there's actually a tremendous amount of complexity in the possible scaling laws in this. And okay, so all of these solutions, I should say, including wave maps and Young-Mills, they were obtained by imposing a symmetry reduction. For example, for the wave maps model, if you impose a so-called co-rotationality reduction, which we learned in Jacek-Gendre's talk, you reduce it again to a semi-linear equation like this, which doesn't have the derivatives anymore. Okay, that simplifies the analysis significantly. Okay, so what is the significance? Why do we care about these? Are these just some kind of freak solutions? No, the significance is that for quite a few of these models, so for example for the wave maps and the Young-Mills, it is understood that these solutions form as the basic building blocks of the general dynamics of solutions close to blow up, for example. So more precisely, if you have a general solution to the wave maps equation, but let's say of energy now above the ground state, then the general philosophy that we have now is that if such a solution blows up, then there are finitely many points. These are these xi's at which the energy can concentrate. And at each of these points, in a backward light cone attached to such a point at the first blow-up time, you have a certain number of harmonic maps which get dynamically scaled and shrink to a point. And there is also Lorentz invariance, so you have to combine this with Lorentz invariance. And the general conjecture is that a solution should in general be possible to decouple the solution into these two pieces, the singular part and a part which remains regular in the energy topology, which converges to something as you approach the blow-up time. Now, something like this, for example, for the harmonic map heat flow, the analog of wave maps, there's something weaker, but analogous was established by Struve in the 80s, where you don't get a continuous in time a representation like this, but along a sequence of times. And the recent work by Stefano Burzio, for example, allows you to extract in a possible singularity scenario at least one such harmonic map. But again, this is only along the sequence of times. And of course, eventually you want to have sort of a kind of continuous time decomposition of your solution. Okay, so now I'm interested in the issue of stability of these solutions, and I think, as far as I know, even for the simple, the basic examples that we now know of actual blow-up solutions of this form, which have one bubble, finite time blow-up solutions, the full stability properties outside of the symmetry reduction are not yet known. And it seems that the present approaches have run into some issues with this. Okay? So this is actually a very interesting problem, which people in this field are aware of, and there's some debate actually if they actually are stable, or if there are some kind of strange obstructions going on. But even within the restricted symmetry classes, such as co-rotational wave maps, establishing stability of these kind of blow-ups is a very delicate issue, as I will try to explain now. So to explain this, basically I have to refer to the two methods that have been developed to to actually build such blow-up solutions. And as far as the energy critical equations that I've displayed before are concerned, there are basically two approaches that have been developed. One of these approaches is by the school around Franck Merle and Pierre Raphael, mostly Pierre Raphael and collaborators, who have managed to apply this method to lots and lots of examples, in particular these energy critical wave equations. And on the other hand, there has been an approach developed by Schlag-Tataru and myself, resulting in quite different kind of dynamics. And so to compare these two, so the Merle-Raphael approach typically gives stability of the solutions as a byproduct of the construction. On the other hand, for the Schlag-Tataru solutions and myself, so this information was missing from the construction, and this was very unclear, sort of like if they have any good stability at all. And moreover, as I've said, like so these Schlag-Tataru solutions, KST solutions, they don't have a fixed blow-up rate. They come with a continuum of rates, and also they are not C-infinity smooth. They can be made as smooth as you want, but always finite degree of smoothness. So typically this kind of blow-up rate corresponds to smoothness h1 plus nu. So if you choose nu large, they get more and more smooth. But if nu gets small, they get more and more close to energy regularity. On the other hand, in the Merle-Raphael approach, you automatically work with C-infinity data. However, the blow-up rates which they obtain usually is uniquely determined. All right, so there are all these differences between these types of solutions. And so let me give a sort of very ridiculous sort of quick sketch of the method that gives the Merle-Raphael solutions. So both the Merle-Raphael and the KST approach consist basically in two steps, roughly speaking. You first build an approximate blow-up solution, and then you complete this approximate blow-up solution to an exact solution. And in the Merle-Raphael approach, this approximate solution, this is typically called Q sub B. So the Q sub B, you start with the rescaled ground state, say, and you add certain corrections here. The Ti are solutions of certain elliptic problems, and B is a parameter which corresponds to lambda T over lambda squared, which is not determined a priori. Which I guess it can be sort of approximately determined, the correct speed from this approximate ansatz, but the exact scaling law is then determined in concordance with the remaining radiation part. And so in this expansion here, you can't, typically the number of terms in this expansion is very rigidly determined by the problem that you're dealing with. For example, for the co-rotational wave maps, there is exactly one correction that you have to impose, and then you pass to the next stage. So then once you have this approximate solution here, then you add the radiation part and you try to force this to become a precise solution. And to get control over the remaining epsilon here, you impose certain orthogonality conditions on epsilon. This is kind of where B comes in, like by choosing B suitably, you force the orthogonality here. And then you use some kind of energy methods, typically by writing down the correct energy type functionals for epsilon, differentiating this functional, and you derive some sort of virial identity. And this virial identity then satisfies certain remarkable positivity properties typically, which are in turn hinged to monotonicity properties of this parameter B here, of the function lambda. I mean, this means positivity properties of the parameter B. Okay, so this is very roughly in a nutshell. So then at the end of the day, the evolution of this B, which means lambda, and epsilon is sort of studied at the same time. Now, for the KST method, it's very different. You fix the blow-up speed to begin with. So you say lambda of t is a function like this. And then you try to build an approximate solution. And by contrast to the Merle-Raphael method, here you can add as many terms as you want. You can make this approximate solution as accurate as you want, in the sense that by adding sufficiently many of these VIs, you can make the error as small as t to the n, where n is any large number. And again, like these VIs are gotten by solving suitable elliptic problems. So let me not get into the details of how this is done. Let's just assume that this can be done. And then in the second step, you try to complete this approximate solution to an exact solution. So you add an epsilon to it. And the epsilon solves a certain wave equation. And it turns out that the wave equation which epsilon satisfies, there are certain linear terms in the source, which are very bad. And to deal with these linear terms, what saves the day is choosing this n large enough. such that basically integrating this function t to the n over time gives you a 1 over n gain, and thereby we can make sure that, that the equation for epsilon can be bootstrapped and you get good control over the epsilon. Okay. So now this whole method, because it relied on a lot of corrections to be added, and then basically to control epsilon, you had to force vanishing of epsilon at the blow-up time. So the impression that we got is that these solutions are very, very unstable potentially. Probably there may be some like high codimensional manifold of perturbations which still, I mean, along which you maintain this kind of blow-up, but the idea was that it's probably generically very unstable. And the point of this talk is actually to kind of disprove this last point and kind of to explain a new way to think about the stability problem of these kind of blow-up solutions, particularly the KST blow-up solutions. And the upshot is going to be that the stability, of course, this is intuitively natural, the stability of these solutions depends on the nu. And if you choose nu small enough, meaning that your blow-up scaling parameter is close enough to the self-similar t to the -1 rate, these solutions are actually as stable as can be. Okay? So at this point, we can do this for the energy critical focusing nonlinear wave. We can't do it for the wave maps yet, but our belief is that the same method should be applicable to the other models as well. And so let me talk now a little bit about this box use minus u to the 5 model in 3 + 1 dimensions. And I will always look at radial solutions, so I'm not studying the stability under general perturbations yet. Now, so this problem, it has some disadvantages compared to the wave maps model. The conserved energy of this model is not positive. So the conserved energy here is energy of u is integral 1/2 del Tx u squared minus 1/6 u to the 6. So clearly it doesn't have a definite sign. And this non-positivity of the energy means that these bubbling off blowups are actually not the generic kind of thing that happens for this model. There is another sort of much more trivial type of blowup, the simple ODE blowup, which is what you will observe if you model this equation on a computer. And these ODE type blowups are known to be stable in a very strong sense under radial perturbations, say. They're stable under perturbations which are small in the energy topology. So this is a recent result by Roland Donninger. But then there's also, as I said, there are these funny static solutions, W of x, over-Talenti solutions. And these can be perturbed to result in this family of KST bubbling off blowups with these scaling speeds. And so these were constructed by Schlag-Tataru and myself in 2009. I guess, well, that's when the paper was published. And then there was originally a restriction on nu bigger than 1/2, and then Schlag and myself improved it to all positive nu later on. Okay, so now it's the stability of these solutions that I care about. Now, as I said, so these solutions, they're not C-infinity smooth. The data are only of smoothness h1 plus nu halves. And this has to do with the choice of approximate solution, and more precisely the choice of the second correction, the second elliptic correction. And I will get back to that later at the end of my talk for a technical reason, but okay, let's just accept this. Now, compared to Mel-Raphael method, so interestingly, that method has not yet been implemented for the 3 + 1 dimensional critical focusing wave. It has been implemented for the 4 + 1 dimensional analog by Hilaire and Raphael in 2010. And as usual, they get a unique blow-up rate, T inverse times e to the square root log t. You see that this expression here grows slower than any negative power of t, but faster than any power of logarithm. So it's some kind of interesting, very close somehow to these polynomial rates that we have there. And they have C-infinity data, and moreover, they assert in this paper that these blow-ups that they construct are stable for radial perturbations along a codimension 1 Lipschitz manifold. And this codimension 1 Lipschitz condition is very easy to explain. Okay? So this has to do with simple spectral properties of the linearization around W. So now let's go back to the 3 + 1 dimensional context, where the KST solutions are the only thing we have right now in terms of finite time blow-up. And so as I said, so there's the energy is not positive definite. And this means this is the reason why one has to distinguish between two classes of solutions for this model. There are so-called type 2 solutions. Those are the solutions for which the H1 norm on the lifespan of the solution is a priori bounded. I mean, it's a priori, it doesn't become arbitrarily large. And type 1 solutions for which the supremum of this H1 norm is infinite on the lifespan. So the example of a type 1 solution would be the ODE blowup. An example of type 2 solutions are W, the static solution, small solutions which scatter to 0, or the type 2 blowups by KST. Now, you can sort of abstractly consider type 2 solutions for this model. And at this point, there is a very complete classification of radial type 2 solutions due to Deukertz-Koenig-Mell. And I probably don't have to go into a lot of explanations here because Carlos Koenig has lectured very extensively about this. So brief, any type 2 solution, either if it exists globally or just finite time blow-up, decouples into a sum of scaled ground states, Orban-Talenti solutions, plus an error term, which converges in a suitable sense as you approach the blow-up time. And okay, so this result says nothing about the stability of these types of dynamics. It also doesn't say anything about the actual occurrence of any solutions of this form, other than the W itself, say. So at this point, what do we know? Well, we know that there are such solutions with one bubble, the KST finite time blowups. There are also infinite time blowups. There are infinite time vanishing solutions where the W gets larger and larger and larger. And there are solutions which converge, of course, to W, but which are not equal to W. But other than that, as far as like two bubble or other dynamics of this model are concerned, these are not known yet. They are known in higher dimensions due to work of Jacek-Gendre. Now, what I'm interested in is the stability of type 2 solutions if they have one profile. And there is a result here due to Nakanishi, Schlag, and myself, which is actually very similar to the result which Collot mentioned on the heat equation in high dimension. And it says the following. So let's assume that you take a type 2 solution which has one bubble. So this can be a solution which exists globally, or it can be a finite time blow-up solution. And assume that it decouples into a bulk part and a small part, a radiation part, and assume that on the lifespan, the radiation part, let's say, has very small H1 norm. Then you can construct a codimension 1 Lipschitz manifold, sigma, passing through the data of the solution at some time before blow-up, say, such that if you start with data on this Lipschitz hypersurface, you get a type 2 dynamic. If you start with data above this hypersurface, you get blow-up. So there's always going to be blow-up above, but we can't quite say at what type of blow-up that is. And if you start with data below, then you get scattering to 0. And above and below is exactly the same way that Collot discussed in his talk. It's determined in terms of like multiples of the unstable mode of the linearization around W, which you add or subtract from your data on sigma.
Can you say that this manifold is actually C1?
Well, it's Lipschitz in the, no, not yet, I don't think so. Yeah. But, so this is a construction in the energy topology. And this means that as far as the dynamics on sigma are concerned, there is basically nothing you can say. Because even if you take this manifold through the actual ground state W0 data, there is like a huge complexity of possible dynamics for small energy perturbations of W. So you can have finite time blow up, you can have solutions which blow up in infinite time, you can have solutions which blow up, which vanish at infinity, everything in a small energy neighborhood of W0. So if you work in the energy topology, there's not much more that you can say here. So if you want to establish, let's say, stability of one of these KST solutions for perturbations along sigma, you have to work in a different kind of topology, in a stronger topology than the energy. Okay. Okay, so again, like the codimension 1 is simply a fact that the linearization around W of my equation has a unique negative eigenvalue, which leads to exponential growth. And you always need to impose some sort of orthogonality condition to this unstable mode to ensure that your things don't escape away somehow. Okay, so now the goal of what we wanted to do was to analyze the stability properties of these KST solutions along this hypersurface sigma. And of course, one thing that you could have done is try to implement the method due to Mel-Raphael, try to use these energy type methods. However, so what we wanted to see is if the methods that were introduced in the work by Schlag-Tataru and myself are actually powerful enough to give you also stability. And what was important to me was to sort of understand, get a method which is maybe conceptually, as far as I'm concerned, slightly simpler, that you don't rely on miraculous positivity properties of these amazing quadratic expressions which you get after many integrations by parts and things. Maybe there is a way that's conceptually simpler, which explains which of these blow-up solutions are stable and which ones are not. Okay, and all right, so the result is this. This is due to Stefano Burzio of EPFL and myself. So let nu be sufficiently small, then the KST blow-up solutions are stable along a codimension 1 Lipschitz hypersurface of radial perturbations in a suitable topology. Okay, so this is optimal, this result, and this is the analog of the Hilaire-Raphael result in higher dimension. Now, again, you will say, okay, so maybe this is strange because, I mean, if I can perturb this, then maybe I could now produce C infinity solutions, but I can't, because the perturbations are always smoother than the solution which you perturb around. So you're stuck in this rough class. You can't get out of it. Okay? So, now, the same method can be used for larger nu, but if you increase nu, then these become less and less stable. So then you get some simple linearly growing nu number of conditions which you have to impose. And maybe it's, I don't know, it's maybe natural because, so the first time that I encountered this kind of thing was in numerical work by Piotr Bison, which goes back to 2001, where he looked at the co-rotational wave maps. And what he observed was, I mean, very, maybe naively, you take some Gaussian initial data and you increase that with an amplitude until you suddenly get blow up. And then he observed that there are basically two scenarios. One was like a sort of an unstable threshold blow up, bubbling off blow up. And that corresponded to something like lambda of t was some power t to the minus 1.2. And then he had stable blow up, which corresponded to something like lambda of t is t to the minus 1.1, something like that, okay? But so it seemed like you could see that somehow, like if there is some kind of news, if this nu here is small, then you're stable somehow, and if it's large, then it becomes a threshold phenomenon. And this kind of result would somehow explain something like this. Of course, the solutions are not smooth here, okay? So that's a drawback. Now, so another way of saying this, what this result says is that if you impose optimal stability property on type 2 blow up, then this does not single out a single blow up rate. Okay, so there's infinitely many. However, what is a very reasonable conjecture is that if you impose C infinity smooth data, then you will get a quantized set of blow up rates. And this is very natural because this is then, if you impose infinity, this is sort of like in a heat flow example where it's known. I mean, you only get this quantized set. So in other words, this KST solutions are truly hyperbolic phenomenon, right? And they are, for nu small enough, they're actually stable. So very interesting. Now, okay, so let me, in the remainder of the time, let me try to explain to you. So what was the idea behind proving this result? So basically, you proceed very naively. You start with a specific solution, as in the KST work. So it's a W, a scaled bubble, plus the remainder, which is small in a suitable sense. And so this U specific, I want to perturb it. So I'm adding an epsilon to it. And if I do this, then I will be willy-nilly, if I do this sort of naively, in the equation I will get this operator, this linear operator, which has a time-dependent potential term. And of course, what is slightly scary is that this potential term not only is time-dependent, but it becomes singular in finite time. So you have this concentration going on. And so the idea is basically to first kind of look at this linear problem here, and to kind of use an iterative method to solve the corresponding equation. And already at that stage, what will turn out to be important is you get some sort of, it's like a Dyson series that you get for the corresponding solution. And what will play a role in the convergence of this is the monotonicity of lambda actually comes in. That will ensure convergence. But at that stage, if you just study this problem, like what exactly lambda is not very important. However, this becomes important in the second stage when you then solve the corresponding nonlinear perturbation problem. And it is there where the proximity of lambda of t to t inverse, in other words, the smallness of this nu is going to come in. And one will see very clearly exactly what the condition on nu is. To control the nonlinear terms, you need something like nu is less than 1/3. It's nothing, not extremely small. It's something very, very simple. And then, well, I mean, this sounds nice, but the issue is like there are certain vanishing conditions you have to enforce to make these first two steps work. And they're very easy to explain. One is the discrete, the exponentially growing mode. You always have to enforce that. That's why you will have always codimension 1 for these things. The other one is a resonance. There is a resonance, which is simply, well, I mean, that comes from the scaling invariance of the problem. Well, the resonance is del lambda, w lambda evaluated at lambda equal 1. And for this problem, this resonance, so it's not an L2 eigen function, it's weaker, it's only a resonance. However, this resonance also leads to growth, and this growth has to be controlled by a second vanishing condition which we have to impose. And this second vanishing condition is something that I've talked about a year ago at ESGS. So now the question is, how do you get back of the second vanishing condition? But this is very natural. Typically what you have to do is you have to modulate, you have to exploit the scaling invariance, time symmetry, translation invariance. But there is a catch here in this problem, and that's because these KST solutions are extremely rigid. Because if you translate them around, or if you scale them, it turns out that compared to the original solution, you add something which is very rough. And it is too rough compared to the topology that you have to work with in this previous stage. So these things, they just sit there and you can't move them around. So how do you get out of it? Well, the thing is you have to sort of infinitesimally modulate in lambda. And here you use a flexibility in the scheme of approximate solutions that we used in the work with Schlag-Tataru. You don't have to use lambda as t to the minus 1 minus nu. You can add small power corrections in this. It's very flexible. Using that, you can enforce this vanishing condition that controls the resonance growth, and then you're good. So, okay, so now let's go back. So the first step, you have this horrible linear operator with a time-dependent potential term. Okay, so here's a generalization of this. Now, in general, I don't know, I mean, maybe I'm just being too ignorant, but I don't know if there are good techniques for dealing with something like this. The closest that I could find in terms of a general strategy is an announcement by Marius Beceanu, who looked at operators of this form, which are intriguingly close to what occurs in this problem. So basically, he imposes some sort of compactness of this family V of Tx up to scalings. And he says that then he can prove some sort of Strickhouse bounds, whatever, but he has to assume that there are no eigenvalues or that there are no resonances. And so we always have these resonances, so this is not going to work. So what can we do? Well, I mean, we just do it with our bare hands, which doesn't result necessarily in the most elegant way, but it results in a way to do it. So how do we do it? Well, I mean, to start with, let's go back to basics. So I'm looking here at this operator. So this is the operator which arises when you multiply everything with R, then you translate a 3 + 1 dimensional problem to a 1 + 1 dimensional problem via radial. And you obtain this linearization. And so there is this unstable eigenmode, and there's the resonance, which you can compute explicitly. It looks like this. So for a 1 + 1 dimensional operator, a resonance is simply a zero, a function which gets killed by the operator, which is bounded, which this function is. And correspondingly, so this is all the work by Schlag-Tataru and myself furnished these relations here. You have a corresponding Fourier expansion. You can expand a general L2 function in terms of this unstable mode and the continuous spectral part. And so there's these general eigenfunctions, generalized eigenfunctions. And each of these generalized eigenfunctions, it decouples. It can be written as the resonance plus an error term. So this representation is useful as long as r squared times psi is small. And if r squared psi becomes large, then these things start to oscillate and they start to look like the standard Fourier bases. So you see there's the resonance sitting in here, and this is like a key aspect. So then let's multiply everything by r to go to a 1 + 1 problem and introduce new coordinates, which is standard, which is also done in the Raphael ansatz. You introduce this variable tau, which is the integral of lambda. So lambda is t to the -1 minus nu for me, and I introduce the new variable r. And then you get this wave equation here. And you see, of course, the gain in this is now that the operator L is actually now time independent. It has like no longer the time dependent potential. It's just this thing here. But the price that you're paying, of course, is that here the time derivative gets replaced by these nasty expressions here, these dilation type operators. And so beta nu here, okay, beta nu, this variable is just lambda dot divided by lambda, which is basically 2 tau to the -1, which is going to be important for my discussion. Okay, so here's the equation. N of epsilon is all the nonlinear terms. And the idea is to translate this sort of problem to the Fourier side. Solve this in terms of the Fourier expansion. Okay, so what happens? Well, the problem is, of course, first of all, that RdR phi is not xi d xi. So this is what makes the free wave equation so simple to solve, and the potential is not so simple to solve. You get these nasty error terms due to this, and in fact, if you translate things to the Fourier side, this non-equality introduces certain non-local integral operators, so that at the end of the day you have some sort of differential integral equation, which is not obvious to solve. However, these non-local terms come with weights in terms of this beta nu. And it turns out that somehow, miraculously, one can iterate these things away in a suitable way. Although, like, at first sight, it seems like they could kill you. But it turns out that by iterating sufficiently often, you can get rid of these things. Anyway, so here is what happens. So if I introduce this Fourier transform of my epsilon tilde variable, then I get the left-hand transport operator, where d tau looks like this. So again, it's like some kind of dilation operator. And so x underline means there's always, it's a vectorial quantity. There's the discrete spectral part and the continuous spectral part. The discrete spectral part has a tendency to grow exponentially. To avoid that, you have to impose a codimension 1 condition. Once you impose that codimension 1 condition, it becomes uninteresting. It's well behaved. So the issue now becomes to control the continuous spectral part in this. And on the right-hand side, you have these nasty non-local integral operators, which come from what I just explained. And you have the Fourier transform of the nonlinear terms. So again, so you can write down these non-local integral terms in this way. And you see particularly scary is the first one here. There's a beta nu tau in front, which is like tau inverse. So if you integrate that in time, you just break even. So it's not obvious that you can actually close and gain smallness for these things. That's kind of what's scary. But anyway, here's the animal that you have to deal with. Okay. Now, okay. So f again, so these are the nonlinear terms. And so now the idea is to solve this x equation by an iteration scheme. And it will turn out that if we impose essentially 2 vanishing conditions on the initial data, then we can get something which converges to something good. So how is this done? So to begin with, you look at the 0th iterate. So you forget about the source terms, and you just get this transport equation here. And for the continuous spectral part, I can solve this thing explicitly. You get this formula here. Okay? So tau, again, remember tau is the variable which is the integral of lambda of s ds. So as t goes to 0, t approaches blow up, tau goes to infinity. So now you're trying to solve this problem from some time tau 0 to time infinity. And if you compute what lambda is in terms of this new variable, you see it's tau to the 1 plus nu inverse. And in particular, if nu becomes small, this becomes a very large power of tau. So in particular, if you look at the weights that you have out here, these weights grow very quickly. This looks horrible, right? They might kill you. I mean, you can't get anything out of this. However, I don't really care so much about this here. I care more about the function that's represented on the physical side. So I compute the corresponding, so this is the Fourier mode, and I compute the corresponding function epsilon tilde when substituting this. And the key here is that you can write the phi, the Fourier mode, as the resonance plus something, which is somehow better. And of course, correspondingly, you can write your epsilon tilde as a multiple of the resonance plus something which is in some sense better. And you compute what this function c of tau does. So the entire problem comes from this c of tau and how much it grows. And if you do the computation, you see generically the C of tau is going to grow like t to the 1 plus nu inverse. And that's terrible, because that means my epsilon tilde is going to grow. And if I put that in the nonlinearity, I lose all control. So I want to prevent that growth. And it turns out that, okay, so I write down two vanishing conditions on x0, x1, the data, but you can combine them into one condition, really. By imposing conditions on x0, x1, you can force this parameter c of tau to grow at most linearly. And these conditions are very simple to write down. So here are these conditions. These are, of course, here you use the exact form of lambda, but you can, in all of this, you can replace lambda by a different law. And instead of nu tau 0, you would have lambda times the integral from tau to infinity of lambda. That's something very simple. Okay, so all of this generalizes. And if you impose these conditions, then you get this here. So now you get at most linear growth. So now I say, now I can explain how to kill the nonlinear terms with this. This is harmless, because if now I choose nu sufficiently small, I can control the nonlinear terms. Why is that? Well, I mean, remember, these nonlinear terms, they come with this weight, lambda to the minus tau, 2 of tau, times the nonlinear terms. And lambda to the minus 2 of tau decays very quickly, the smaller I choose nu. On the other hand, if epsilon tilde grows only like tau, then the nonlinearity grows like tau to the 5. So if I choose nu small enough, I kill it. I have no problems from the nonlinearity. This is where the condition nu is less than 1/3 comes in this part. So this deals with the 0th iterate. But now I need to go to the first iterate. And the first iterate solves this equation. Okay, so I look at the DML term. And particularly scary is the DML term that comes from these non-local integral terms. Okay, it looks like this. And again, you see, so I don't want to change my data at time 0. I don't want to mess with that perturbation. So I write it like this. I don't integrate from tau to infinity as we did in the original work, because then I have no freedom to, I'm going to destroy the original perturbation. I don't want that. So I write it like this. But then again, you have these terms here which grow. Now it turns out that this kind of thing, if you work in the right norms, when psi is large, you're fine. There's no problem. The issue, always small frequencies, because small frequencies translate to this resonance, which is going to grow. So how can I deal with this issue? Well, the idea is that I sort of break this integral into two pieces. Integral for small frequencies. I take the integral from tau 0 to infinity, and if I put the integrand in there, that is again a solution of my free transport equation. And then I subtract the integral from tau to infinity, which is now like in the KST work, which is now fine for small frequencies. I don't have problems because these weights, lambda of tau divided by lambda of sigma for this term are controllable. However, now I have this term here, and this term is a solution of the free transport equation, and it no longer satisfies the vanishing condition which I needed. So what do I do? Well, now I have to take advantage of this R. This R has structure, and it has special vanishing structure, and these vanishing structures are evidenced in the work with Schlag-Tataru in this Duke paper. And the idea is that, well, I'm forcing the vanishing condition by adding another solution of the free transport equation. And you will say, okay, well, then I mess up my data again somehow. But, well, I mean, remember, it's just an integral condition, so I can choose these guys in a very special way. So specifically, the way I choose these are Fourier transforms of a cutoff of my resonance. So this is really kind of the analog of modulating, but translated to the Fourier side. And then you will say, but maybe this is large. Somehow you add something large. But the beauty is that, no, it's small, actually. So if you work in the right norms, then these corrections here are much smaller than the original correction by a factor tau 0 to the minus 1. And so now this means that, okay, you start with your perturbation, which satisfies some codimension 2 condition. And then you have to add a little something to control the next step, but the little something you add is much smaller. But then it's not scary because then I can do implicit function theorem at the end of the day and I still get an open set of things. And then you preserve this throughout the entire iteration scheme. You always, at low frequencies, you get a decomposition of your Fourier mode into a good part and a free part where these corrections that you have to keep adding decay more and more and more. And at the end of the day, this whole process converges. Of course, you have to do work with suitable norms. And okay, so these norms are not so pleasant. They're basically like this. They're energy type norms. So this weight psi to the 1 plus corresponds to a 3/2 regularity, and you also have to penalize things at small frequencies again because of the resonance. So you use a norm like that. There's also a little bit of leakage in terms of growth, whatever, and then there is sort of a square sum over dyadic dyadic times that you have to use to control to improve this a little. So these are technical details. Anyway. And then actually to make sure that this entire process converges is delicate because at each iterative step, you don't gain smallness for these non-local linear terms. So to actually force convergence at the end of the day, you have to take many reiterations. And this is actually a method that was introduced in work by Schlag-Tataru and myself on the Young-Mills blow-up. So it's actually a fairly robust method by now, but in this context, it's most powerful and most natural somehow. Okay, so what is the upshot? You get some intermediate theorem here. So there's a codimension 2 Lipschitz manifold of perturbations, such that if you take your specific blow-up solution with a fixed lambda, and you add this perturbation, then you get the same type of blow-up. And so the question is, how can I get rid of one of these vanishing conditions, which you remember is due to the resonance, the growth of the resonance. And so this is where kind of the specific structure of these KST solutions becomes important now. So, so the issue is how to get rid of this, how to do some sort of modulation theory, how to replace your original U-specific by a time translate or by a rescaling. And like I said, there's some problem here because of the roughness of these solutions and the fact that they propagate a shock along the backward light cone. And this makes them extremely rigid objects. And so, okay, so I mean, to be more precise, so this has to do with the approximate solution that one starts out with. So there are these corrections one adds, which solve certain elliptic problems. And the choice of these corrections actually is such that for V2k, so the even corrections, they have this structure here. So for example, when you put k equal 1, then you get this 1 minus a to the 1/2 nu plus 1/2 terms. A is r over t. So at the light cone, these are very rough if nu is small. And if you rescale these things, or if you time translate them, you shift them by an amount which is infinite in my norm with which I work. So this is not going to work. However, so what you do is you do sort of an infinitesimal modulation change. You replace your lambda by an expression like this. And it turns out that with this more general lambda, you can still do the same construction as in the original KST work. And moreover, so now you get a family of blow-up solutions that look like this. And okay, so if gamma 1 and gamma 2 vanish, then this coincides with the original KST solutions. Otherwise, they are slightly more general. And then there is this simple modulation step that says that if you take a perturbation here, you add it to one of the original KST solutions, then I can write it in this way for pseudo gamma 1, gamma 2, where now the new perturbation here, with respect to this solution, satisfies the vanishing relation with respect to the resonance with respect to this new scaling parameter. And once you do this, you get the optimal stability result. So.
And similarly,
yeah.
Okay. Similarly, you have a spreading solution.
Yeah.
You work with the Dunninger.
Yeah.
So, does it work for this?
I think so. It should work because I mean this is just by analogy to the heat flow result. So there's a recent result by Del Pino and those guys, and they get the same phenomenon, and there is codimension 1 stable. Okay. So I believe that it should also work.